This is section 12.2 from the Integrated General Chemistry book from Sapling, and the title is Properties of Liquids. That is sort of a vague title because it's kind of general, but in this particular case, when it comes to properties of liquids, we are exploring three properties in particular, which are the viscosity, the capillary action, and the surface tension. And these properties I like to see in more like a behavior. It's something that you can observe liquids doing, and the origin of these properties, of these behaviors, is the intermolecular forces. Okay, so liquids exhibit these behaviors because of the intermolecular forces. Okay, so and we're gonna explore what all these properties are. So again, to remember what a liquid is a condensed state, condensed because those particles are close enough that they can interact with each other, but because it's a liquid, then these particles are moving constantly. In a solid, all the particles are in a fixed position relative to each other. In the liquid, they are still close enough that they can see each other, but they can move freely. They can go past each other. Okay? So these intermolecular forces will originate these properties. As I said before, the ones that we are interested in are the viscosity, the surface tension, and the capillary action. Okay? So viscosity, simply put, viscosity is a resistance to flow. Probably the best way to see this is imagining that you want to pump a certain liquid through a pipe. Then the viscosity is a measure of how easily you can pump this liquid through the pipe. So the higher the viscosity, the more difficult it is to make this liquid to flow through the pipe. It will require more energy, and at some point you may require a different input to facilitate the flow of this liquid. So as I said initially, this viscosity has its origin in the intermolecular forces, but in the particular case of viscosity, then we also have an impact on temperature. Remember, it's a resistance to flow. Those particles are moving. If you increase the temperature, you are increasing the energy of those particles, and those particles will be moving faster, right? So if you want this liquid to move through a pipe, the higher the energy these particles contain, the easier will it be for them to move through the pipe. So things to remember here then is that if you have a higher temperature, then the viscosity will decrease. So let's put it this way. Higher temperature, low viscosity. But since it's resistant to flow, the larger the intermolecular forces between the particles. Remember, if the intermolecular force is larger, then it means there is a higher attraction between the particles. And what it really means is, well, the particles don't want the other ones to go anywhere. They want them to be close to them. So that's why the resistance to flow increases. They don't want their friends to go anywhere. Okay, so if the IMFs increase, then the viscosity also increases. So careful here, because the impact of temperature and IMFs go in different directions. So increasing the temperature will decrease the viscosity, but increasing the IMFs will increase the viscosity. So be careful with that part. So since this is about intermolecular forces, then you can predict based on the structure, based on what intermolecular forces you can either identify in a group of molecules. Then you can predict, okay, this molecule is supposed to have a larger viscosity because it has stronger intermolecular forces. So things to pay attention to here. We have water. We're comparing here water with hydrogen peroxide. They look pretty much the same. They have oxygen, they have hydrogen. They are molecules, neutral molecules for that matter, so there will be dispersion forces. It's hydrogen and oxygen. We already know enough about these two elements as to say that the bonds between them are polar. And we know that water is polar, so pretty much hydrogen peroxide is also polar. Okay? Moreover, there is hydrogen, the hydrogen is attached to an oxygen, there is oxygen, the oxygen has lone pairs. So in these two cases, they are both polar molecules. So we have dispersion forces because they are molecules. We have dipole-dipole because they are polar molecules. And then we have hydrogen bonding because they met all the requirements for hydrogen bonding. So we agree that in this particular case, hydrogen bonding would be the strongest intermolecular forces, no matter how you look at it. So now how do you determine which one of these will have the strongest IMF? So the way we determine that is, if you remember shape of the molecule and points of contact when it comes to determining the strength of the intermolecular forces, we can apply a similar approach here. So let's put it this way. So if we have a water molecule here, and then we have another over here, okay, we can establish an interaction between that hydrogen and that oxygen. And why not? We can have an interaction between that hydrogen and the oxygen. So pretty much you can say in this particular case, as simple as we can do it, there are 2 points of contact. There could be more. That's perfectly fine. But let's keep it simple here. If we look at the hydrogen peroxide, though, we have hydrogen, oxygen, oxygen, and hydrogen. Your oxygens will have lone pairs, and we are going to put, what I'm going to do is I'm going to put the hydrogen here, oxygen, oxygen, and hydrogen. And now I'm going to establish where are the interactions. So the oxygen, the hydrogen will be attracted to that oxygen, but there is no limitation in regarding how many oxygens can attract that hydrogen. We tend to put it one-on-one, but I mean, that oxygen would be jealous enough that he wants to interact with that hydrogen, right? The same thing happens here with this hydrogen, with this oxygen, and with that oxygen. So you actually have multiple points of contact between the hydrogen peroxide molecule. So we can still trying to keep it simple. We can say, well, there is 1, 2, 3, and 4 interactions here, whereas in the case of water we only have 1 and 2 interactions there. So because you have multiple interactions, or let's say higher number of interactions in the hydrogen peroxide molecule compared to water, then yes, you have hydrogen bonding on both, but the IMFs are stronger in the hydrogen peroxide molecule. Okay, so if we determine this, then that means hydrogen peroxide will have a higher viscosity compared to water. Okay, so here we are not doing anything too different from what we have done before. Okay, so we are just determining what are the intermolecular forces present in each one of these molecules. We determine what intermolecular forces are stronger, and then you proceed to analyze, well, when we look at the properties, because these IMFs are stronger, then the property will be such and such. This case is viscosity. The larger the IMFs, the higher the viscosity of that liquid will be. Now, surface tension. Okay, it's still it's attraction, right? So, but surface tension, as the name implies, it has to do with the surface of a liquid. So, what is going on in the surface of a liquid? Well, if you look at, let's go directly to the picture. Okay, because the surface of the liquid looks different than the, let's say, the center of the liquid. Okay, we are focusing our attention on this molecule right here. Okay, in the center of the liquid, that molecule is completely surrounded by other molecules, so it's interacting with multiple particles in all directions. So let's say at some point it's kind of a I don't want to say the word static equilibrium, but there is no net force applied to this molecule, so there is no reason for that molecule to go anywhere. You know, there is no force pulling in one particular direction. In other words, you can think in terms that because all these forces are pulling in all directions, the resulting vector of all those forces is zero. So there is no net pull in any direction for that molecule. It's surrounded. The pull is equal in all directions, or at least we assume that is the case. So nothing happens to that molecule. Now, if you look at the surface, okay, if we take a look at the surface here, above the surface, there is nothing. That is not entirely true because there is air, but when it comes to, we are focusing our attention on the liquid, so there is no liquid above the surface, right? So there is nothing pulling this molecule in any direction, okay? So then you have the sideways molecules, but the ones that are right below and are pulling that molecule, this molecule, the one at the surface, is being pulled more strongly downwards. So it's being pulled to, think in terms of, they want to take this molecule below the surface, so to speak. It doesn't happen because of the other molecules that you have present there, but that's the net pull on that particle. So that means if you want to pull this molecule, if you want to take it out, then it gets a little harder. If you want to, you know, make your entrance into the surface, it gets harder because those molecules, the ones at the surface, are more strongly attracted to in the direction of the liquid. Okay, so that's pretty much what happens with surface tension. So what are the results of having this behavior, surface tension? Well, that's something that you commonly see in everyday life. Okay, the drops that water form in the rain or on surfaces. If it's a wax surface with grease or anything, well, the water will form kind of perfect droplets, okay, round. But if it's another type of surface, like in glass, then they will tend to flow through the surface because, you know, there is more affinity to that kind of surface. Okay, more on that later. So, if it's wax, because it's non-polar, there is no affinity. The water is polar, right? So, the water, because there is not much affinity for that wax, then the water will tend to be close to each other. So they don't want to go anywhere but stay close to each other. Okay? So here, with a hexane or gasoline, it's a non-polar substance. The intermolecular forces are much weaker, so they will tend to, you know, form spills and produce a fine a thin layer on the surface. Okay, water would not want to do that. So let's put it this way: if you have if you spill water on the floor and you spill gasoline on the floor, well, the water will travel the gasoline will travel faster because those molecules are not strongly held together. Okay, there is nothing preventing that molecule from going farther away from the other molecules. Okay, pretty much that's what surface tension means. Now we are talking about these molecules moving, flowing, and interacting with surfaces. So in that case, if we are talking about the liquid and the interaction of a liquid with a surface, then we have to identify or differentiate those forces. Okay, they are intermolecular forces anyway, but whether the forces are between the liquid molecules or between the liquid molecules and the surface molecules. However, we want to make a distinction between the cases. So whenever we are referring to interaction between the same particles, between the particles of within the liquid, we refer to those forces as cohesion forces. Okay, and again, don't get me wrong, cohesion forces are still intermolecular forces. Okay, now we are making the distinction that this cohesion is between same particles. It's intermolecular forces between same particles. Now, when we are talking about adhesion, it's the same intermolecular force principle, but here we are talking about different particles. I should be maybe more specific. Same particles meaning same substance. And here we are talking about different particles because they are different substances. Okay, like in the case of the liquid and the surface, they are different substances. So cohesion is between the same substance. Adhesion is between different substances. Okay, so that's the main difference between those two. Still, there are intermolecular forces involved in these two. It's the same principle of intermolecular forces. It's just between how are these molecules interacting, and we need to define this because now we are talking about capillary action, and capillary action basically is the ability of a liquid to travel against gravity. Remember, gravity makes everything fall down, right? Everything that goes up has to come down. But liquids have the particular characteristic that if they are flowing through a very narrow tube, a very narrow pipe, so to speak, they can do that against gravity. And the reason for that is because of these intermolecular forces. So capillary action basically is the ability of the liquid to flow against gravity. But there are certain requirements, okay? It has to be a thin tube. And the reason for that, and this is, I'll come back to this later. Yes, let's talk about this figure first. The thing is that because through that pipe, through that tube, the molecules of the liquid are interacting with the surface of that tube, then depending on how strong those intermolecular forces, those adhesion forces are, then it will make it easier for the liquid to climb up through that tube. So in this particular case, glass is made of silicon dioxide in essence, so to speak. And silicon dioxide is SiO2, right? So we have a bunch of oxygens there. And the oxygens here will have available lone pairs that can interact with the hydrogen in the molecule, hydrogen in the water. Okay? So basically, between the water and the walls of this glass tube, you have strong adhesion forces because you have sort of hydrogen bonding. Okay? Now, hydrogen bonding between different substances do not require that you necessarily have hydrogen in the other molecule. So if you have a hydrogen attached to oxygen, nitrogen, or fluorine in one molecule, and then in the other molecule you have an oxygen or a nitrogen or a fluorine with lone pairs, they can perfectly form hydrogen bonding, okay? Hydrogen bonding between different particles, meaning different substances. So that's what's going on here, okay? This is hydrogen bonding between different substances. So in a way, these adhesion forces, because it's different materials, are strong, and basically what water is doing here, water is climbing up the tube with the help of these strong intermolecular forces with, or adhesion forces with, the walls of that glass tube, okay? How far they can go? Well, it depends on how strong these adhesion forces are. But the narrower the tube is, the more favorable that climbing is. So the water can travel farther away, farther up the tube if it's narrow enough. Now the case that you have in the other side, this is mercury. Now mercury is an atom, right? It's a metal, it's a liquid metal, it's an atom, it's a large atom, therefore it's very polarizable. Therefore between the mercury atoms there are strong dispersion forces as intermolecular forces. But it's just dispersion, it's non-polar, right? It doesn't have hydrogen, it's just a single atom here. So there are no very strong intermolecular forces between mercury and the glass walls in that tube. There's another possibility for that. You can think in terms of the glass tube being kind of polar, or with the possibility of forming hydrogen bonding, but mercury doesn't have that possibility, okay? It would be attracted through dispersion forces, because after all, every single molecule will have dispersion forces. But here, mercury will not have any interest in climbing up the walls in this tube, because there are no strong enough adhesion forces. In this case, for mercury has stronger cohesion forces, okay? Therefore, the end result here is to demonstrate that the shape of this meniscus, and the meniscus is the surface, the shape of the surface of that liquid when you put it in a tube. So for water is concave, and for mercury is convex. Okay, so they are in different. They have different shapes. That's it. Okay. So now, why is capillary action important? Well, if capillary action wasn't a thing, wasn't a property of liquids, well, there is no way that plants could do what they do. Okay, they absorb water through the roots. How is it possible that from the ground all the way up here, you can transport water? Okay, there is not a pump there. Well, actually there is, but you are not providing that much energy for that water flow to go upward. But you are using the properties of this liquid. You are using capillary action to your benefit. You are using capillary action to reduce the energy that you require to transport water up the tree. Okay? So how do you help the trees and the plants in general to do so? Well, once water reaches the leaves, so to speak, well, there is transpiration. And transpiration, what it is? Well, when you are sweating, you are just releasing water through your skin, right? Well, pretty much plants do that. And when they get rid of that water, think of that is your pump. That is what is establishing the need to transport more water up the tree. So the combined action of transpiration and capillary action is what makes water flow upward in that tree. And water being transported to every single cell in the tree. Okay, so that's one of the main importances that you can see in capillary action. Now we talk about the meniscus. The meniscus is the shape of the liquid surface when it's put in in a tube. Okay, if you form strong intermolecular forces with the walls of the tube, then the meniscus is going to be concave. If not, it's going to be convex. Okay, and these are your two cases, water and mercury. Now, let's think about these three substances, right? So we want to rank the surface tension in this, right? We were talking about capillary action, that's fine, but now we are focusing in our attention again on surface tension, and we want to rank these substances as liquid because all of these are pretty much gases at room temperature. So we want to picture them as liquids, okay? That's perfectly fine. And determine which one will have the largest surface tension, okay? Or ranking lowest to highest. So what is the lowest? Lowest surface tension. And again, surface tension depends on the intermolecular forces. The stronger the intermolecular forces, the higher the surface tension. So the lowest surface tension means we are looking for the IMFs that are the lowest, and therefore the highest surface tension belongs to the one with the strongest intermolecular forces. So that's our mission here. We have three substances. We have to determine which one. Let's put it this way. If you can rank these substances according to the strength of their intermolecular forces, then you can perfectly do so in terms of their surface tension. Okay, so we have nitrogen. Whether nitrogen is in the liquid form or the gas form, the formula is the same. We already know enough about the nitrogen molecule to know that this is nonpolar. Okay, and that's pretty much enough to say that the only thing that you see here in this molecule is dispersion forces. Okay, if we look at the HF molecule, hydrogen fluoride molecule, well, it's hydrogen and fluorine. There is nothing more electronegative than fluorine. So pretty much everything that you connect to fluorine will give you a polar bond. So this is a polar molecule, which means you have dipole-dipole, but this molecule is also special because you have hydrogen attached to a fluorine, then you have fluorine with available lone pairs, so this molecule will also exhibit hydrogen bonding, and hydrogen bonding will be the strongest intermolecular force. If you compare hydrogen bonding to dipole-dipole, the hydrogen bonding wins. It would be stronger. And when we go to HBr, then this molecule is polar. You have hydrogen, but you don't have oxygen, nitrogen, and fluorine, so there is no hydrogen bonding. Therefore, there is dipole-dipole interactions only in this molecule. Okay, so if we rank the molecules according to their intermolecular forces, if we are going from lowest surface tension to highest surface tension, then we are going from weakest intermolecular forces to strongest intermolecular forces. So in this case, dispersion forces, let's change color here, is the weakest. Hydrogen bonding, the strongest. So we have nitrogen will have weaker intermolecular forces than hydrogen bromide, and hydrogen bromide, weaker intermolecular forces than hydrogen fluoride. So that is the order of increasing intermolecular forces, and it just so happened that is also the same order for surface tension. So liquid nitrogen will have the smallest or the lowest surface tension, and hydrogen fluoride liquid will have the highest surface tension. Okay? In summary, remember, these properties of liquid have their origin in the intermolecular forces. I like to see them more as a behaviors because you have to see kind of something happen. It's not really a static property. I mean, you can see the property in action. Okay, so the properties are viscosity, surface tension, cohesion and adhesion, but that has to do with capillary action. Okay, the viscosity, one thing to remember with viscosity, something that you have to be careful with viscosity, is that yes, it's controlled by the IMFs, but also by the temperature. Okay, in the exam we will try to be specific enough in terms that you don't have to worry about if the temperature is this or let's put it this way, we are not giving you a case in which you have to analyze those two factors together. Okay, we either give you one and keep the other constant or vice versa. Okay, usually we will focus on the intermolecular forces, and we want you to analyze everything from the point of view of intermolecular forces, so we might leave the temperature out of the discussion. It does affect, and the only thing that you have to remember is that if you increase the temperature, you decrease the viscosity of the liquid. Okay, surface tension also increases with the strength of intermolecular forces. Okay, and the capillary action, remember, we have cohesion, means same particle, same substance, and adhesion, that means different. Okay, and different is, let's put it this way, we have the liquid and the surface. Okay, it's an interaction between the liquid and the surface of another material. Okay, depending on how the balance of those forces are, you will have a larger capillary rise or a lower capillary rise. Okay, so that's it for now.